In this module, we will consider free body diagrams. When we are working problems where multiple forces are acting upon an object, it is often useful to draw the objects isolated from its surrounding and showing all of the forces acting on the object. Now, currently, we are considering objects to behave as if they have no extent. Only the magnitude and the direction of the forces acting on the object are important. In the future, when we consider extended objects in rotation, the position on the object where the force acts will become important. But this is something that will be relegated to a future module. To understand free body diagrams, we want to consider some examples. So first of all, consider a television sitting upon a desk that sits upon the floor. We ask the question, what forces act upon the television? Well, first of all, there's the force of gravity from the Earth acting down, F sub g1. Second, there's the normal force from the table acting up. We'll call this N sub T1. Now, our free body diagram we might draw by showing the object in whole with the forces acting on it. But because we're considering this just to be a point particle, we might simplify it down to just the two forces acting on the point particle. All right, so we have from this the two forces, force of gravity and the normal force acting on the object. We can write down their sum, and this sum from Newton's second law will be equal to the mass times the acceleration. But this is equal to 0 because we know the television is sitting still upon the table. It has no acceleration. Now let's consider what forces are acting upon the desk. Well, again, there will be the force of gravity acting down on the desk. There will also be the normal force from the floor acting up against the desk, keeping it from pushing through the floor. We'll call this normal force N sub F, or N for the floor. And finally, there's also the normal force from the TV acting down. This is the action-reaction pair force, which is paired with the normal force of the table acting up on the TV, that's N sub T1, and it is equal and opposite to the normal force from the TV acting down on the table. Now, we can draw our free body diagram and reduce it to a point, and again, write out Newton's second law. The sum of all the forces is equal to mass times acceleration. In this case, once again, the acceleration of the table is 0 because it's sitting still, because it's sitting on the floor and not falling through it. All right, let's make things a little bit more difficult here. What happens if someone pushes from the left on the TV with a force F sub P? Well, we now need to draw this force on our other diagrams, so we can do that. And we also have to update our laws of motion, our versions of Newton's second law. Now, in this case, I've simply added a second equation. Now, let's be a little bit careful here. You can't always do this. I'm adding a separate second equation because the force of gravity and the normal force are acting in the vertical direction, and the force of somebody pushing is acting horizontal at 90 degrees to this. So these forces don't have any contribution of one on the other. They're in perpendicular directions. So I can reasonably write these as separate equations, but in reality it might be a better thing to write them together, as we'll see later. But here, just to keep things a little bit simpler, we're writing a second equation, which shows that because I'm pushing from the left with a force F sub P, the TV is now going to accelerate. Okay, and that acceleration is going to be related to the force by the mass of the television. All right, well, as I push the TV, eventually it's going to lose contact with the table, at which point the normal force from the table onto the TV will go away. And now it's actually simpler just to go ahead and write Newton's laws of motion, the second law, as a single equation, where the sum of the forces is now just the force of me pushing and the force of gravity on the TV. And this will result in the TV still accelerating, but the acceleration will be different. It'll be due to the sum of these two forces. The normal force from the TV has also disappeared from the table, and this means that the normal force from the floor up on the table needs to reduce because the total force acting down is now less, and so we need less force acting up to keep the table from accelerating. Of course, also, because there's no normal force, the TV will fall and shatter. Let's consider a second example. Here we have a block of mass m on a frictionless inclined plane. What forces act upon the block? Well, again, there's going to be the force of gravity acting down, and there will be a normal force from the plane acting perpendicular to the incline. We'll call this N. We can draw the free body diagram here using the entire block, or reduce it to a point with the two forces acting on it. But again, what we're going to find is that from Newton's second law, the sum of these two forces is equal to the mass times the acceleration. Here we have to write this as a single vector equation because there is a component of the normal force acting in the same direction as the force of gravity and vice versa. We can't cleanly separate them because they're not perpendicular to each other. Now, we need to break up these forces into components. And a useful direction to choose is the direction of the incline, because we know that the acceleration of the block perpendicular to the incline will be 0 because the normal force will always act to keep that acceleration 0. So it's useful to pick our coordinate system and our unit vectors to be parallel and perpendicular to the incline. So we'll pick them as shown in the diagram. Now, we're going to be able to decompose our components in terms, or our vectors in terms of these unit vectors. And to make life a little easier on us, let's make the diagram a little bit bigger. And first of all, the normal force we can simply write as the magnitude of the normal force times the j hat unit vector. We know it's acting in the j hat direction. And the acceleration we know is going to be acting parallel to the plane in the I hat direction, so we'll write it as the magnitude of the acceleration times I hat. Notice that this means that a positive value for the acceleration means that the mass is accelerating up the plane. That's not really physically reasonable for a mass on an incline. We know it's going to slide down the plane, which means it should be experiencing, if we do everything correctly, a negative acceleration. And finally, we can use the incline or the angle of the incline, which is 30 degrees, and correctly transfer that to our diagram, and then decompose the force of gravity into its components. And now we have all the different forces and the acceleration written in terms of components. And we can now write out Newton's second law in terms of the components. And considering, first of all, the I hat direction, we can read off from this equation that minus mg sine theta is equal to the mass times the acceleration along the incline. And from the j hat direction, we see that the normal force minus the mass times the gravitational acceleration times cosine 30 degrees is equal to 0. So the j hat equation will tell us the magnitude of the normal force, and the I hat equation we can solve for the acceleration. All right, let's consider a third example. In this case, we have a mass hanging from a set of ideal ropes. First of all, what is an ideal rope? Well, an ideal rope is massless and supports a uniform tension along its length. Now, because it's massless, this means that the rope will not sag under gravity, so it will remain straight between the points where it touches other objects, like the ceiling, or where it joins a vertex with other ropes. Now, in this case, there seems to be no reason to define a coordinate system and our unit vectors to be in anything but the horizontal and vertical direction, so let's choose that. And we can now draw a free body diagram for the mass m. It will have the force of gravity acting down minus mg j hat, and a tension caused by the rope pulling up on the mass. We'll call this T sub 1 j hat. And from Newton's second law, T1 minus mg equals 0 because it's 0 because the mass is not accelerating. We're assuming that the rope is not stretching or breaking, so the mass hangs in place. We can then also draw a free body diagram for the vertex where the ropes join together. Okay, once again, we're going to have the tension in that vertical section of rope. It's going to be minus T1 j hat. Well, it's minus T1 because we have an ideal rope which supports a uniform tension along its length. So because we know the tension was T1 at the lower end of the rope where it attaches to the mast, it's also going to be T1 at the upper end of the mast where it attaches to the vertex, but here it's going to be pulling down, whereas at the bottom it's pulling up on the ball. Tension is always pulling, it never pushes, so it acts in the direction shown. There will also be a T2 and a T3, T2 for the rope at the angle on the right, and T3 for the rope at the angle on the left, pulling in those particular directions. Now, we can transfer the angles over to a diagram where we want to decompose these forces into their components. We can easily do that using a little bit of trigonometry, and we can show that T2 and T3 have the given decompositions in terms of components and unit vectors. And now, if we write down Newton's laws for, first of all, in the horizontal direction for this diagram, we're going to find that T2 cosine theta minus T3 cosine phi is equal to 0. In the j-hat direction, we have minus T1 plus T2 sine theta plus T3 sine phi is equal to 0. And we also have the equation from the free body diagram for the mass itself, which is that T1 is equal to minus mg. So we can eliminate T1 from the vertical equation above. This leaves us two equations with two unknowns, the two tensions T2 and T3. And given two equations and two unknowns, we can solve this to get the tension in the two ropes.